Relativity is something you do cover in grade 12 to some extent. Okay, that's kind of good to know. All right. In that case, what was I saying? I was saying the exact same thing this morning. Let's say it again. Yes. So today I'm going to plan on talking a little bit about the theory of special relativity. And first I'd like to start by talking about why it's actually such an important and useful thing in so many contexts, especially in physics and especially in modern physics. This has to do with what the theory itself is about. And so I'll just quickly preface what it kind of concerns me. The special theory of relativity is really about trying to think of how do we make observations of time and position. So if I see something happen somewhere at some point in time, well, how is this process of me observing that actually happen? And when you think about it, that's actually an incredibly deep idea, because whenever you measure something like at all, almost always, or at least as far as I've thought about it, you are essentially making a position of time and measurement, for example, of time and position. So for example, let's say in grade 11 you guys have done a lot of kinematics, right? You want to verify like Newton's laws and whatnot, and you want to do an experiment where you throw a ball off a cliff. You can write down the equations for it, and you want to see, well, how long will it take for the ball to fall down, right? Well, to do an experiment like that, to verify that your equations are correct, you will have to make a measurement of the point in time when the ball hits a certain point, right? Well, that's a measurement of time and position. Or, for example, if you were to do something with electricity and maybe circuits, I guess now you have all of these digital devices that let you do measurements. But if you were to go back, so say to the 60s, in the end you'd be also looking at some device like this, where you have some subdivisions like 1, 2, 3, 4, 5, and you would have like a dial, and you would be looking at the position of the dial at a certain point in time. So even in this case, you're still measuring the position of something at a certain time, which is why the theory of special relativity is so fundamental to all of physics, because really it talks about, like, it is somehow related to practically any experiment that you can think of. Now, of course, we'll see later that even though it's related and it somewhat affects every measurement in some sense that you make, we'll perhaps see that often its contribution is not that significant and not that important, and that will make sense when I talk a little bit more about it. So, okay, that's a short intro to what I'm about to discuss. Let's see. Let's before I start talking about the theory itself, I think we should quickly discuss what a theory is in general. Like, what is a theory? Like, why are we here? And that's a question for the audience. So what is a theory? You can give me a one-word answer. You can give me a half-word answer. Yeah. Yes, person in the back.
I guess we can make using evidence.
Okay, so what is a theory? Let's say it's some kind of guess. Okay. Okay. Using some evidence, you said, right?
Yeah.
Okay. Anybody else? Any other suggestions? Yes.
An idea that has an overwhelming amount of evidence.
Okay, an idea with a lot of evidence. Okay. With a lot of evidence. Evidence. Okay. Yes?
Something we haven't disproved yet.
Something, oh, I like that. Something we haven't disproved yet, yes. Something not disproved. Okay. Well, the truth of the matter is that depending on who you ask and their own personal philosophy, they will give you a different definition of what a theory is or what a theory might be. So I will give you kind of these. None of these are technically wrong, because you can always kind of reframe your thinking to go about it. But I'll give you kind of my third-year understanding of it, which is perhaps a little bit too utilitarian, but it reveals a few interesting ideas about how we think about science. So, in my understanding, a theory is as useful as what we're trying to do with it. right? At the end of the day, why do we need a scientific theory? Well, because we have some kind of process, and it's not even that we want to describe it, right? It's, in some sense, we do want to understand how it works. But at the end of the day, we want to apply it to something, and we want to make a prediction, right? I want to say, hey, I have these initial conditions. What is going to happen after this much time? Or something like that. I want to be able to make a prediction. So in that case, you can sometimes think of a theory as some predictive device, right? It's just something that you can use to make a more or less accurate prediction, and then you can check, does this prediction agree with nature? Does nature do the same thing as I expect it to, or does it not? And for example, oftentimes you can have multiple different theories which look very, very different, but they give you the same prediction. For example, you guys may have heard of the Bohr-Rutherford model of the atom, right? Mm-hmm. And then in your chemistry classes, maybe you've heard of the Schrödinger model of the atom, right? They're very different because the Bohr-Rutherford model of the atom, well, it's you have some nucleus and then you have like electrons going around the nucleus in some orbits, versus the Schrödinger model of the atom is something more complicated where you have like these electron clouds and whatnot. But actually, both, if you look at the specific case of the hydrogen atom, you get that the energy levels that these two models give you are in fact numerically the same. They give you the same energies for the different orbitals. And so in that sense, in that specific case, these theories give the exact same prediction, but this one's a lot easier to do calculations with than the Schrödinger one. Now, of course, if you were to look at some other properties of the hydrogen atom, okay, then the Bohr-Rutherford model gives you the wrong predictions, and okay, then we know that it's not entirely correct. But I guess in some sense it's useful to sometimes think of a theory as, hey, well, this is just a predictive device. It's not necessarily exactly what might be actually happening, but this gives me a good prediction, so perhaps there is some truth to what I'm saying. And that's exactly why I really liked something not disproved, is because in that sense, a theory isn't something you can actually ever prove, because hey, if I say, I'm only using this to make some prediction about the future of some process, well, that's not necessarily something that's ever true. That's just, okay, I'm getting some number that's close to the number that we observe in nature. And so in that case, a theory can only ever be wrong, and it can't ever be right. But okay, more on that later. That's a little bit of a, kind of side, getting sidetracked a little bit here. So the question is, how do we structure a lot of theories? Well, this is useful because we're about to go through this process ourselves. So we want to make some prediction. Well, if you want to make some prediction by perhaps doing a little bit of logical reasoning, you have to start somewhere, right? If you want to make some logical reasoning from somewhere to somewhere, you have to start knowing something. So okay, that means that we need to start off with some assumptions. So we need to start with some assumption, right? And then if we have some assumption, it's not quite natural to see, well, if I assume this is true, what else is true, right? So we have to look at some of the consequences of our assumptions. We compute the consequences. And after we've done that, we looked at our assumption, we studied it a little bit, we figured out if this is true, what else must be true. Then, well, that's essentially, we've made some prediction about how the process we're studying works. And in that case, I should actually check if my prediction is correct and do an experiment, right? And hopefully my experiment maybe works with my predictions and confirms my prediction, or and hopefully confirms my prediction, or maybe it doesn't, and then I have to modify my assumptions and keep going until I run out of funding or get tired. So this is the general idea of what we're trying to do. So okay, let's start actually talking about the theory of special relativity, hopefully, and not the Bohr-Rutherford model of the atom, because that's not what I'm here to talk about? Well, we need to, first we need to state the assumptions of the theory. But before we do that, I need to give a few definitions. So we have a little bit of terminology that we can work with. So let's start with the first, I want it on this board. I think I want it on this board, that's fine. So we're going to start with the first definition. I said that the theory of special relativity has to deal with kind of measuring something happening at a certain time and in some place. So it makes sense to define some kind of coordinate systems. So I'll just say a reference frame. So definition. A reference frame is a coordinate system. Coordinate system for time and space. Okay, that's good. So what do I mean by this? Well, you've all seen like regular Cartesian coordinates many times. You have your x-axis, you have your y-axis, and you can write down a point and it has some coordinates. You can represent your point with some coordinates x, y. But oftentimes, we don't just care about the position of something happening. We also care not where something happens, we also care where and when something happens, right? For example, you can be sitting in this desk at like coordinates, I don't know, -10 at 2 p.m., but then 3 hours later, you're going to be somewhere else, right? So it makes sense to also think about a coordinate of position and of time to kind of fully describe something happening, right? That makes sense. And when I say reference frame, all I just mean is some coordinate system. Okay? That's one thing. Now I will give a second definition. I'm actually going to have to look at this one just in case. So another definition is an inertial reference frame. An inertial reference frame. Hopefully my handwriting is somewhat visible. If not, I can start like doing typed writing. So this is a reference frame. A reference frame in which an object with no net force on it, an object with F net equals 0 moves at a constant speed. At a constant speed. So let's think about constant speed. Let's think about what this means for a second. So suppose I have some object that has no net speed on it. Let's say this water bottle. No net force on it. Let's say this water bottle. So from my reference frame, this water bottle is stationary. And let's say I'm standing here, and I have my own clock to measure time, and then I have some kind of notion of like I can think of me being at the origin of my reference frame, and I can assign this every position that I see a coordinate, and I also keep time. So okay, this is stationary in time with me. But then if I had Miss Rafi run from that side of the room to the other side of the room, right? She has some other kind of, at a constant speed, she has some other kind of reference frame relative to herself, right? As she would be running, she would see all of you, she would think of herself as stationary, because according to her, the origin is at 0, 0, she's always at 0, 0. She would think of herself as stationary, and of you guys as moving this way, right, relative to her. And so in that case, if this water bottle has no net force on it, we want this water bottle to not accelerate, right? Ideally in an inertial reference frame. So then she would see the water bottle moving at a constant speed relative to itself. But that is only if she ran herself at a constant speed. Which is why, in some sense, when we talk about inertial reference frames, we're really talking about reference frames which are moving at a constant speed relative to each other. Because if one reference frame was accelerating relative to each other, that means whatever stationary object in that reference frame has to be accelerating in this one, and that's already not what we want. We want things that have no net force to be moving at a constant speed and not accelerating. So we're talking about reference frames which are, in some sense, moving at a constant speed relative to each other. Okay, So that is, now that we've gotten these two definitions out of the way, we can write down the assumptions of the theory of special relativity. They're often referred to as Einstein's postulates, because, well, he came up with them. Postulates. Okay, so there are technically more of them, but we'll really look at two of them, because they're kind of the main ones, and the other ones are a little bit more subtle. We'll maybe be kind of using them, but fine. The first one is all laws of physics. Take. Whoops. What am I reading? Take the same form. Form in all inertial reference frames. Inertial reference frames. Okay, and the second postulate is light propagates with a constant velocity, with a constant speed, c, as observed from all inertial reference frames. Inertial reference frames. Okay. So these are the two postulates. Let's briefly stop and kind of think about them. So we have the first one, we have the second one. Okay. So the first one isn't too bad. What's the first one saying? The first one saying is, suppose I was observing some physical process and I wanted to write down an equation for it, right? Of how I'm observing it. And then, once again, we have Mr. Rafi still running from that side of the room to this side of the room at a constant speed. Somehow, because if objects for me with no net force are moving at a constant speed and objects for her with no net force are moving at a constant speed, then we would expect that the equation that I write down about what I'm observing and the equation she writes down about what she's observing should really be somehow, they should look the same, right? Because really, why would there be any difference in how we observe something just based on who's running which direction and how fast, right? That shouldn't matter too much. Perhaps we'd be plugging in different numbers into our equations, that's true, but the equations themselves should still be more or less the same, right? So this postulate kind of makes sense why we're assuming this, right? This I kind of understand, right? We don't want one observer to be observing different physics from another observer. Okay, now the second one's a lot less obvious as to why we assume it, and because of that, we want to draw a picture for it. Yes. Okay. I think I will then erase this top bit. And I will avoid erasing this for a while. So let's draw a picture. What's our idea here? Our idea here is as follows. So let's say we have a person standing here, and they're just standing. And they have eyes and they can see stuff. And then we have another person over here, and this person is running this way, and they're holding a flashlight. Yeah, this is like a very large flashlight. And this flashlight has some light coming out of it, right? And this person, let's say, also can see stuff, and they are traveling this way with some speed v. Okay, and this relative to this person. So, okay, what would we expect classically? Classically, since this person's the one holding the flashlight and running with it, they'd look at this light, and this person would see it travel at, say, speed c, the speed of light, right? Now, classically, we would expect this person to look at this flashlight and say, well, if this flashlight, the flashlight itself is traveling at speed v, there's light coming out of it. So that means the light has to be traveling at speed c plus v, right? Do people agree with this? However, this postulate says, no, 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 absolutely not. This person's traveling at a constant speed v, so this guy and this guy are inertial reference frames. That means that this person also has to observe the speed of light to be exactly c. Both of them. And once again, this is a postulate. This is something that we just assume without without an explanation of like why this is true. We just assume it, and then we look at what else is true if this is true, and then we check if it works out with experiment. However, I think this is a little bit of a very not an obvious first guess to make, right? And a lot of people attribute this, of course, to Einstein's genius, that he has managed to figure out that this is kind of the correct assumption to make, that gives you the right kind of prediction and the right kind of consequences that we do observe in nature. However, oftentimes people skip out the full story of the kind of the history of this assumption, because there is a lot. He didn't just come up with this out of nowhere. Probably there were small hints that this might be true that people kind of noticed in different parts of physics since like the mid 1800s. And I'm actually going to briefly show you one of such examples. I think you guys haven't done too much electricity and magnetism yet, but I think you should still understand the following setup. So in the 1800s, Maxwell, that was this guy, he wrote down Maxwell's equations, which kind of describe really how forces between, how different charges exert forces on each other, and how perhaps currents also can have like a magnetic field, and how you can have forces due to magnetic fields. So okay, they came up with these equations and started looking at different possible scenarios where they can apply these equations. And one of the scenarios was the following one. They thought of, like, say I have two very large sheets of metal, and they're stacked kind of parallel onto each other. And suppose I have a current going through each one of these each one of these sheets of metal in the same direction. And there's some separation between these pieces of metal. Now, okay, in this case, if I have a current, then actually, I think they also assume that you charge these a little bit to get the current going. So if I have some charge, and it's the same charge on two of these plates, then just because like charges repel each other, well then there should be, on each one of these plates, there should be some electric force, right? That will be pushing it away from the other plate. But then if you look at the Maxwell's equations for a little bit, you'll find out that because there's moving charge, you will have a magnetic field, and because of that you will have a magnetic force that will pull these plates towards each other. And so the question is, these forces may not be balanced, so these plates might be moving away from each other or getting closer to each other. But the interesting question that people asked, well, what can we do to make these forces equal to each other, right? So that the plates aren't moving relative to each other at all. They're just, you have a current in each plate, and they're just standing stationary like this next to each other. Well, they did this calculation, and it turns out, if you want these two plates to be stationary to each other, you want the current to be traveling at a speed v equals c, the speed of light. Right? Why is this a little bit problematic? Well, perhaps we can accelerate our current to the speed of light. Sure, ignore that problem for now. Well, how do I measure my speed? In what reference frame, right? So if I have these two plates in front of me, and in this one there's current traveling with speed c, in this one there's current traveling with speed c, and they're stationary because we computed that in this case the forces are equal. Now suppose I have somebody run past me in this direction, let's say. Oh, actually no. If the current's going this way, let's have the person run in that direction. All of a sudden, that person sees this current travel at a speed greater than c, right? But that means that the forces will no longer be balanced, which is weird, because that means the person running away would see these plates get closer or further away from each other, versus I will just see them as stationary. And that really doesn't make any sense. Like, why is it that one observer would see something accelerate, versus I would see, something be constant, right? Because remember, F equals, in this case, ma, right? And that means if there's some force on the two plates, then there would be some non-zero acceleration. And even though they're running at a constant speed relative to me, they'd still see something accelerate when I'm just not seeing it accelerate at all. That's really weird. So people thought about it, and this was kind of one of the hints that perhaps there's something really special about the speed of light and kind of how we observe things and how we observe the speed of light. But okay, this is kind of a minor aside point just for some background knowledge and something just for fun. So now that we've so now this postulate, we have a little bit of context for it. Like there was other evidence that kind of suggested that this might be true. So we'll just assume this to be true without too much explanation. Okay. Now I've been talking quite a bit about making some kind of measurements of something in at different times, right? So now that we've stated the postulates of the theory, right? We've done the part where we make some assumptions. I think it's time for us to compute some consequences, right? And see if these two things are true, what else can we deduce from this? Right? I said that we should be talking about some kind of time measurement, right? So okay, I want to measure time, and I want to somehow use these two facts to measure time, right? So all laws of physics take the same form in all inertial reference frames. Well, that's a little bit of we'll kind of forget about this one and not worry about it too much. And here we have the second postulate, which talks about light, right? So we have to find a way to use light and the fact that light travels at a constant speed. So we want to somehow maybe use the light or the speed of light to measure time. Okay. Any suggestions on how I could maybe do that? So how could you perhaps not even the speed of light, but just in general speed, how can you use speed to look at time?
Well, we could use formula speed is equals to distance over time. So speed
Yeah.
over distance would give us
Exactly.
no, distance over
Yeah, well, sorry. But the idea is correct. I often like to make the joke that if we want to measure time, we want to use a clock, right? And if we want to add light to that, we should use a light clock. Right? See? And that's kind of the answer. But what you said with using, speed, position, and time, and how they're related, to measure time is a valid idea. I'll erase this now. So we will use this kind of idea to construct our light clock. So suppose I have two detectors, which can detect light. So one at the bottom, one at the top, and they can just detect light. And let's say these two detectors are set a distance L apart from each other. All right. Now, let's say we take a beam of light and shoot it upwards, and then it's going to reflect off of the top detector, and then actually maybe this isn't a detector, maybe this is a mirror of some sort, and then the bottom one's a detector. Sure. So light shoots out from the bottom here, reflects off the top here, comes back down, and hits in the exact same spot, and we detect it. And if we look at the time it takes for a ray of light to go up and then back down, that could be our unit of time, right? We can measure time in seconds, but instead we can measure time in the little time intervals it takes for light to go up and back down. Yes, makes sense. As a way to measure time. So we'll just say let delta t be the time it takes for a beam of light to go from kind of the bottom to the top and then back to the bottom of our light clock. Okay, so this is very good. Now we have something where we can use our postulate to measure time somehow, right? Because it has something to do with light, something to do with speed of light. That's very good. Okay, this idea makes sense of how we can measure time using a light clock. Okay, I'm going to take a sip of water. Give me a moment. So in that case, let's we forgot the second bit. The second bit was inertial reference frames. We really care about inertial reference frames, and we want to see how do you observe time as looking from different inertial reference frames. So in that case, let's get the following setup. We will have an observer standing here. Let's say that's me. And I have my own light clock, so I can keep track of time in some way. And suppose I have another observer on some kind of train cart that's moving at speed v in this direction. And this person also has their own light clock, and they can also measure time with their own light clock. And let's say we have the same light clocks which are both of height L, right? Okay. So the question we're going to ask today is, so let's look at how does this person observe this time interval, right? And then let's compare to that, how does this person observe their time interval? Okay? So instead of looking at my own time interval, I want to look at this person's time interval and compare as to how they see their time interval. And once again, in this case, when I say time interval, really I mean the time between the two events of the photon or a beam of light leaving the bottom detector and coming back to the bottom detector. So really I'm looking here at a time difference of some kind between two events, right? In position and time. Okay, so we have these two different pictures. And let's say this is observer A and this is observer B. So I think I can now move this to the side. And let's look at what observer A sees in their own light clock. Observer A. So this person, they're looking at their own light clock, and what do they see? This light clock is stationary right in front of them, so they see the beam of light go up, and they see the beam of light go back down. Okay? And we said we want to use what? V equals d over t, distance over time. So we want to compute this, so let's first draw a diagram. This is what they see. They see their bit of light go up, and they see their bit of light then go back down and kind of land in the same spot. I said this is distance L. So in that case, we said what? V equals to delta d over delta t. So then delta t should be equal to delta d over v. In this case, what is our speed? What is v?
That's C.
C, that's the speed of light. Okay. So we have something over c. And what is in this case delta d?
L.
Oh, 2L, yes. Sorry, in this case, I don't mean displacement, I mean total distance traveled, right? So, 2L. Okay, very good. So, okay, we see that this guy measures the time intervals, 2L over C. Very good. Now let's look at how observer B looks at the light clock of observer A, right? So this person is watching this light clock on this train cart moving this way V. So once again, what are we talking about here? This is observer B. What is this person really looking at? Well, we said that our delta t is the time difference between two events. So the light leaving the bottom and then coming back to the bottom plate again. So let's say the light leaves the bottom plate, right? It goes up to the top plate, and then it gets reflected at the top. However, from this observer's point of view, because it takes light to travel to the top plate by some amount of time, right? After a little bit of time, this cart moved, right? Do you agree? So the clock must have moved together with the cart, right? That means the top plate, after some time t, is not going to be directly above where the beam of light eventually left off. It will be a little bit to the side, right? So this person looking at this cart will see the ray of light not going straight up, but they will see it go diagonally somehow like this, right? Do you see why? Because they're observing this cart moving along, right? And the light should go up and then bounce back down. But since the cart is moving along, they would see the light go diagonally up to the top plate, because after a little bit of time the clock would have shifted. And then it will go back down to the bottom plate, also a little bit diagonally like this. And very nice. And okay, this is not, let's see if I can draw this better. Okay, and we would expect this triangle, that kind of this is the path of the light that observer B is seeing, right? We would expect this actually to be an isosceles triangle. I think people can agree, because we would expect that the time it takes for the light to travel up should be the same as the time for the light to travel down, right? Okay, does this part make sense why this is what observer B sees of observer A's light clock?
Yeah.
So this is like observer B trying to make sense of how time works for person A, right? Because he's really measuring some time interval for person A, but from his perspective. Okay, so this is how this person sees the light there. Does that kind of make sense?
Yeah.
Okay. Pardon?
That would be longer than no?
Well, that's what we're about to find out. That's a good question. Well, okay. First of all, what do we want to do? We want to use the exact same formula, right? We want to use the exact same formula, but just on this situation. So in this case, delta D is going to be what in terms of this triangle? Yes, it will be the hypotenuse plus what? Plus the other hypotenuse. So, and we said that this should be equal to this, so it should be 2 times the length of this one hypotenuse, right? Okay. So we would expect that this would still be height L, right? Because we're really, in some sense, we're only moving horizontally. We're not moving vertically. So nothing about like anything vertical related should change too much. So that should still be L. Now, we just have to figure out what is this distance. Okay. Well, perhaps it might be easier to figure out what is this whole total distance, which will be twice of this distance. Okay. Well, what's happening here? This is the point where light leaves, and this is the point where light comes back. Do you agree? And we said that okay. So I forgot to define this. So let delta t prime be the kind of time interval as observed by observer B. The interval as observed by B. By person B. So in this case, right, what does this mean? So the proton, the photon left at time 0, and it came back at time delta t, because we said let delta t be the time it takes for the proton to leave, the photon to leave and come back, right? But how can we find this distance? Well, we know that this and this is the same point of the light clock itself, right?
Yeah.
And the only thing that really happened here is just that the light clock moved from here to here. Why did the light clock move from the setup of our question? Because of the velocity of the cart. And it took a delta t prime time to do that. So how far did it go? It went?
V times t prime.
Yes, so this is v times delta t prime. Okay. I'm going to start using a different color chalk now. Okay, well that means that this little half bit is going to be what? What's this half going to be?
V delta
V
t
delta t prime
prime
over 2.
Yes, so v delta t prime over 2. Okay, that puts us in position to kind of try and use this formula again. So we get that delta t prime has to equal to some distance divided by what? Some distance divided by
c.
c. Good. And our distance, we can use now Pythagorean's theorem. That's a horrible bracket. Okay, L. This is L. This is v delta t prime over 2. So by Pythagorean theorem, this side should be
No, square root of L squared plus V delta t prime over 2 squared.
yes, plus v delta t prime over 2 squared. Okay, that's very good. But we have a problem here. I think you might agree with me that I have delta t prime in here, and also have delta t prime in here. I want to have just an equation for delta t prime equals something not in terms of delta t prime. So, okay, we want to solve this equation for delta t prime. How do we do that? Well, we have, this is just delta t prime, but this has a square root on it. If we don't want a square root, what do we have to do? Pardon?
Square both sides.
Square both sides. Okay, so let's do that. Let's do delta t prime all squared is equal to L squared plus, let's quickly, oh whoops, I lied. We forgot a 2 over here. That's actually important, because remember, it was one of the sides, we need to go up and then back down, so you need a 2. So in that case, what we're forgetting is there has to be a 4 divided by c squared, right? Because we squared the 2 and the c, multiplied by this thing squared, which is L squared, plus, let's do 1/4, because that's 1/2 squared, times v squared times delta t prime squared. And close that bracket. Okay. So now let's expand this first. You can notice that this 4 and this 4 cancel out, right? So we get delta t prime squared is equal to 4 L squared over c squared plus v squared over c squared times delta t prime squared. Okay. I want to solve for delta t prime squared, so I want to move all the delta t primes to the same side. And how do I do that in this case? I should subtract what from both sides?
V squared over c squared delta t squared.
Yes. So let's subtract this from both sides. I get delta t prime squared minus v squared over c squared delta t prime squared is equal to 4L squared over c squared. Okay, that's very good. Well, what can I do from here now? Yeah? Yeah, I can factor out delta t prime squared, not to be confused with the delta t. Because remember, delta t is what this person saw. Delta t prime is how this person is looking at this person. Somewhat different things. Okay, so I can factor this out. Delta t prime squared times 1 minus what? Minus what?
V squared over
Okay, v squared over c squared equals 4L squared over c squared. Okay, and now what I want, I just want to solve for delta t prime, so I'll divide both sides by 1 minus v squared c squared, and I'll take the square root. So I'll just do both of those things in one step. And from this, let's write this maybe in red, I get delta t prime is equal to 2L over c times this little factor, 1 minus v squared, square root of 1 minus v squared over c squared. Okay? So we have that formula, and we have this formula. We have that formula and we have this formula. So let's compare a little bit. What does this person see and what does this person see? Actually, no, let's stop. I'll repeat one last, well, not one last time, but another time of what is delta t and what is delta t prime. Because we did some calculations. Hopefully we didn't forget. So delta t was this guy looking at his own light clock, keeping his own time. And this is how he saw the time between the two events of the photon leaving the bottom of his light clock and coming back to the bottom of the light clock. That's how he measured that time. He measured it as 2L over C. Now this guy, he had his own light clock to measure time, and he looked at this guy's light clock. So this guy, they both looked at the same light clock. But this guy was looking at person A's light clock, and he measured the exact same, the distance between the time between the two exact same events of the photon leaving the bottom of the detector and then coming up and going up, reflecting and getting back to the bottom of this same detector. Okay, so they were looking at the exact same object, just in different reference frames. And let's actually make a brief note of where we use the postulate with the fact that the speed of light is constant. Remember, here we said the speed of light is c, as we would expect. And then here, even though we're in a different inertial reference frame, and perhaps classically we would expect the speed of light to be like c plus v, or like something by cos or something by sine, in this case, we still said the speed of light has to be c. And that's where we use like the second Einstein's postulate. Okay, and we got these two equations. So this guy saw his light clock tick for this long. This is like one tick, and this person sees this person's light clock do a tick in this much time. So first of all, the first thing we see is that hey, the answers are not the same, right? So that's already the surprising bit. The way this person feels time is actually not the same as him observing him feel time. So the way time goes for this person isn't the way this person thinks time's going for this person. A little bit weird. Now let's actually see if we can relate these two formulas. Well, delta t is equal to 2L over C. Can we find a 2L over C in here? Yes. And so we can replace it by, we can hopefully replace it just by delta t. And actually, maybe I'll write this, let me think about what am I going to do next. Yes, I'll write it. Actually, wait. No, I'll keep that. I'll keep that here. I'll write down this kind of as the main equation for today that we have derived. So delta t prime is equal to delta t divided by square root of 1 minus v squared over c squared. Okay, now let's perhaps look at this equation a little bit more. First of all, what kind of number is 1 minus v squared over c squared? Well, no, not well. Maybe if you set v equal to 0, then I guess it would be 1. That's fair. But in general, if you have like some reasonable speeds, like a car traveling or a train car, how large would this number be? V squared over c squared. Small. Okay. A less than 1 for sure. So then 1 minus this number would still be less than 1. If you take the square root of that, that would still be less than 1. So we would be dividing delta t by a number smaller than 1. So overall delta t prime has to be greater than delta t. Okay? So this means that this person thinks that time for this person is traveling faster than how this person actually feels it. Okay, so that's the first thing that we kind of notice from this qualitative. The other thing that we notice qualitatively from here is, okay, suppose I kept making v very, very, very large, like arbitrarily large. I could accelerate this cart as fast as I wanted to. What is a problem that we could run into if we make v like incredibly large? You get 1 minus, you can make v squared over c squared. You can perhaps make v greater than c, right? Perhaps. And then you get 1 minus v squared over c squared. Well, now v squared over c squared would be greater than 1. So you'd have a negative number inside of a square root. Well, that really doesn't work. You probably can't do that. And in general, even if you set v equal to c, you would get 0 in here, and you would be dividing by 0, which is perhaps arguably even worse. So from this we can perhaps conclude that nothing can travel faster than the speed of light. Or maybe, other than light, you can't necessarily have anything accelerate anything to the speed of light. So that's what we get. Nothing can travel faster than the speed of light just from this simple equation. So let's go back and look at what we've done so far. So we've made some assumptions, right? We've stated Einstein's postulates, and then we came up with some scenario and did some calculation, and we computed the consequences of this assumption, and we got this formula. That's like our main consequence, right? And as kind of side products of this formula, we got that, okay, nothing can travel faster than the speed of light, and that from different inertial reference frames, you might be observing certain events in some different way. Okay, that's very good. Now, I would like to still discuss this formula slightly, just a little bit more, to kind of see what is it, what these delta t and delta t prime actually are. Because, just so that we have a sense of when we can really apply this formula. So let's look at delta t. Once again, delta t tells me the distance, the difference in time between two events happening, right? And let's look at delta t. Delta t was this picture. So in this reference frame, and as person A observes it, light leaves a point and comes back to the exact same point. So this is the difference in time between two different events that happen in the exact same point of space. They happen at different times, but they happen in the exact same space. For example, you're sitting in this chair today at this time, and on Monday you're going to come back and sit in this exact same chair. Two different events at different times, but in the same place. Yes, you agree? So this is what we will define as proper time. So we are going to give, I think, my class definition. So definition, hopefully people can see this. Proper time between two events is the time as perceived by an observer for whom the events happen in the same point in space. The two events occur in the same point in space. In space. Okay. Do you agree? So in this case, delta t, this is proper time, right? And delta t prime is time as this person's time as observed from some other reference frame. Okay. But you have to realize that this equation only works where delta t is the proper time. So necessarily, whatever events we're observing here have to be happening in the same point in space as observed by person measuring time delta t. Okay? That's an important bit. So we have this third definition. Okay. So we've done assumptions, we've done consequences. What do we have left? Experiment. Okay. So let's see if we can try and perhaps come up with some form of experiment. Let's actually keep this formula in red here. Delta t prime, I'll write it one more time. Delta t over, how much time do I have? Like 15, 20 minutes?
15 minutes.
Okay, 15 minutes. Okay, very good.
But if you lock the doors, we'll have to.
That's true.
We always lock the door at the end.
Good. Okay. So I'm almost done anyway. So now let's look at an experiment. we want to try and think of some kind of physical situation where we can perhaps, this formula would describe something in that physical situation. You agree? So we've just been talking about having a person on a cart and making that cart go really, really fast somewhere. So okay, let's kind of try and think of this same idea of making a cart go really fast. Okay. Well, suppose in the end of the day I have to measure time somehow, and I want to get a result that I can like actually measure, right? I have like the tools that can measure that small of a time difference. So suppose I wanted to get a 1% difference between the time the person on the cart observes and the time that the person on the ground observes, right? So that means I would want delta t prime over delta t to be equal to, say, 1.01, right? So I want just a 1% difference, okay? Well, from this equation, that means that 1 over square root of 1 minus v squared c squared has to be equal to 1.01. So I know what the speed of light is because I can search it up online. And so let's see, how fast do I have to make this cart go so that this is actually equal to 1.01. And okay, you can solve this equation. I think you would get something that v should be equal to the square root of c times 1 minus 1 over 0.01 squared. That sounds, yes, that sounds right. Then you can check this on your own time, that doesn't matter. Now, if you were to plug these numbers in, this would be approximately 0.1 times c. Remember, c is what? 3 times 10 to the not the negative, 3 times 10 to the 8 meters per second. So this is going to be 3 times 10 to the 7 meters per second. Okay. This is incredibly fast. I am not sure if we have any man-made objects that have gone close to this fast. Maybe like one of the Voyager satellites that we sent in like the 80s, 70s are like of maybe somewhat comparable speed, but I'd have to search it up. I'm not even sure that they're going that fast. So most definitely trying to do an experiment by taking something and speeding it up really fast and then putting a clock on it and comparing that clock to my clock, we definitely can't really do that kind of experiment, right? Definitely doesn't work. And this actually is a key point. This explains why it took us slightly under 300 years to go from Newton's theory of relativity and the Galilean theory of relativity to Einstein's theory of relativity. Because look, we need to start off with some kinds of assumptions. We need to get this theory, we need to make this assumption somehow from somewhere. And in general, we see that the consequences of this theory, you can really see the effect of this theory only at really high speeds. Because think about it, if in this equation I have v really small relative to c, but most speeds that we have in our daily lives are quite small relative to c, this would be essentially 0. So this would, for a small v, this would essentially be delta t prime is equal to delta t. But that's exactly what we have for Galilean relativity, right? The clock of the person standing on the ground should work in the exact same way and measure the exact same time as the clock of the person standing on the train car, right? That's what we know from classical physics. And we get that the special theory of relativity for very slow speeds, compared to the speed of light, but a lot of speeds are slow compared to that, you essentially get the equations we're used to. So okay, that's kind of a good sanity check that this theory makes sense, because that means in a familiar context to us, this theory gives us the same result that we would expect it to in a familiar context to us. So that's good. But back to this problem, we want to make an experiment, right? And we see that we need something moving really, really fast to be able to see in any sense the consequences of these theory in a way that we can actually measure them. So if we can't make something go really, really fast, we have to find something that goes really, really fast in nature. And actually, any ideas? Do people have any suggestions of what might be going fast somewhere? Pardon? Yeah, but that's like hard to observe. You want to, well, once again, if you plug in the speed of light here, you have an issue. So our formula doesn't describe that either too much. We want something traveling slower than the speed of light, but still really, really fast. A little bit too slow. But okay, this is actually a difficult question. And in fact, the experiments I'm about to describe, they only did in the 1960s. So Einstein published this paper on his theory of relativity in 1905, and only 50, 60 years later did they actually manage to do this experiment. I think there may have been a few experiments slightly earlier that did confirm this theory, but this was, I guess, one of the ones I find rather interesting. So we'll talk about this one. And the experiment was as follows. In the 20th century, they discovered these particles called muons. Actually, it was like not muons, I'm lying. Mu mesons. So they have this particle called mu meson. And turns out that these mu mesons are flying towards our Earth from outer space at very high speeds. So if you were to look at the Earth, you have a bunch of these little mu mesons traveling at the speed of about 0.994 times the speed of light. So they're going essentially as fast as we want them to go. And turns out the muons have, so this is their speed. And turns out the muons have a half-life of 1.56 microseconds. So sorry, 1.56, sorry, is that micro? So 10 to the negative 6 seconds. 1.56 times 10 to the negative 6 seconds. And okay, what does this half-life really mean? Let's briefly review that. Half-life means that if I have, say, 100 particles, after tau time, I will only have half of those particles left. So if I have 100 mu mesons, after 1.56 times 10 to the negative 6 seconds, I'm going to have 50 particles left. After another 1.56 times 10 to the negative 6, I'll have 25 particles left, and so on and so forth. Well, of course, this works a little bit better for like when you have a large amount of particles and you can actually divide by 2 in a nice way. But this lets us write down a very nice equation. So the number of particles after time t is given by the number of particles I have initially, right, times 1/2 to the power of t divided by my half-life tau. I think you guys have seen this, but also let's briefly understand what t over tau means. T over tau tells me how many times does tau fit inside of t. So it really is telling me how many times do I have to do this halving process, right? And well, if this gives me the number of times I have to do the halving process, then putting 1/2 to the power of the number of times I have to do the halving process, you're just multiplying by 1/2 that number of times, and well, that's exactly what you would expect the equation to give you. We know it gives the right result. Does this equation make sense? I think you guys should have seen it. Very good. Okay. So then the experiment continues in the following way. There was this Washington mountain. This was actually done by a group at MIT. I think the people working on the experiment were David H. Frisch and James H. Smith. I wrote down their names. That's all I can tell you about them. And what they did is, they're like, okay, we can put a detector at the top of the mountain and count how many particles reach the top of the mountain. Okay? And this mountain is, I think, about 2 kilometers tall. So 2 times 10 to the 3 meters. And then we can put a detector at the bottom of the mountain right here. So here they counted the number of particles at the start. And here they can count the number of particles after they've gone through the mountain at some time t. Do you agree? So, okay. Let's kind of compare what we would expect and what special relativity would tell us. Okay. So, we want to see, let's first do what we expect from just our perspective as people standing down here on the ground. Right? So we would expect these mu mesons to travel this distance, and we can perhaps take the time it takes for them to travel from the top of the mountain to the bottom of the mountain, stick that into that formula, and given n naught, be able to predict nt, right? Okay, so we would expect that the time that we observe for these mu mesons to go from the top to the bottom, well, they're traveling at that speed. That's the distance they travel. So delta t prime should be equal to 0.994 divided by 2 times 10 to the 3 times c. Do you agree? Wait, is that that's the distance? Whoops, it should be the d over. This should be the other way around, right? It should be 2 times 10 to the distance over speed. Sorry, divided by 0.994 c. Yes, I think that's correct. Okay. Now, what's the question?
What's the T over, what is it?
Oh, tau? Tau is the half-life.
Oh, I see, okay.
So the time it takes for the sample to decay, half of it to decay. Right, so if I have 100 particles, after this much time, only half of them are left. And so T divided by tau tells you after T time, how many times did the particles half themselves. And then you can plug that into there and get the number of particles you should have after time T. If they decay at half of them decay every tau time. Now notice, this is delta t prime, not delta t. Why? Because we said delta t is proper time. For proper time, we would be measuring two events that happen in the same place. For us as observers standing somewhere here and looking at this mountain, the events that we're looking at is the mu meson hitting here and then hitting here. These happen at different times at different places, so this is not proper time. Do you agree? This is as how we observe the mu meson. So then we can perhaps plug in this delta t prime into that formula. And if you were to do n of delta t prime, you would get, and you plugged in tau equal to 1.56 10 to the negative 6, and you plugged in these numbers, you would get that only about 5% of the particles you detect at the top should reach the bottom. Do you agree? Yes. Well, you just plug it in and, okay. Hopefully my math is right. Now, but we know from special relativity that how we observe the mu meson's time is perhaps not how the mu meson observes its own time, right? And in fact, we know that we think that more time passed for the mu meson than actually it did for the mu meson from their perspective. And this is the kind of key question. Why would the mu meson decay according to the time we observe it at? It would really care about the time that it's observing for itself, right? The mu meson would be decaying according to its own schedule, not the schedule that we impose on it by just looking at it, right? Doesn't make any sense. So the time that we should be putting in here should be the time of the mu meson. Do you agree? Well, let's look at what does the mu meson see. The mu meson is there, has its own reference frame. It's at the origin of its own reference frame, and it sees this mountain fly at it at speed v. And for it, the two events are the mountain being at 0, 0, so at the mu meson, and then the mountain being and then the mountain, the bottom of the mountain also being at 0, 0 in the reference frame of the mu meson, right? So that means these two events happen at different times, but at the same place, at the mu meson. And that sounds like proper time. So then we can use this formula and we can compute delta t to be equal to this delta t prime, so this one, times this factor of 1 minus 0.994, right? Because, 994 squared, because v is 994 c. So if you plug that into v squared over c squared, the c squared cancels out, you're just left with 0.994 squared, okay? And now if you were to plug in delta t into this equation, you get n of delta t. This would actually give you approximately 70% of n0. And that's a huge difference. Actually, perhaps it would make better sense if I gave you the, did I compute the actual times? Maybe I did, maybe I didn't. Okay, no, I didn't write down the number. I'm not going to compute what delta t and delta t prime actually are. You can do that numerically in their own time and see how these times are actually, they're different by like a whole order of magnitude or something. But you see that this is quite a significant difference. Classically, we would expect that only 5% of the particles live to get to the bottom. But in this case, we see that a whole 70% of the particles get to the bottom. And that's what they actually did this experiment. They had a plate at the top, they had a plate at the bottom, and I think it was something like this that they actually saw a lot more particles hit the bottom of the mountain than you would expect. Simply because the muon decays on its own time scale rather than whatever time scale we observe by imposing. And that's the end of my talk. Hold on, let me just turn this off.